And so with this, you can start the discussion of the human aspects of technology. The first element is the psychology of technology, okay? So if you go most of the presentation, they have some kind of slides that look like this. Performance will continue to improve, and cost will come down. And you can see one thing, all these points, they all look the same. So in any company, everybody fights to be the manager of the next technology. Nobody wants to do a technology that's 2 generations out because you have no idea if you'll be successful. So it's bound to happen that it takes about 20, 25 years, between inflection points. So the normal engineer worked for about 30 years. So typically people see one inflection point. Now, I built my first vacuum tube radio in 1958 and my first transistor radio in 1963. And I hated integrated circuit. I took them off and I wanted to reconnect them myself, okay? So that was a negative progress from my point of view. So what happens, move. Okay, so typically what happens, since nobody wants to pay attention to a technology that is 2 generations out, you run into a problem. Now, this is okay. If that's what happens, it would be okay. What happens actually is very bad. What happens is, somebody goes to the boss and says, boss, you know what? I think we can stretch it. It's going to cost a little more. The performance is not be as good, but I can make it. We can make it. You promote it. You go, good, this is really great. And so instead of doing the right thing, that is really to do something new, we waste 5 or 10 years trying to bang our head against the wall. I'm going to show you that's precisely what we're doing in this moment. So first of all, I want to make sure that there are, hey, is that the battery almost out? Okay. Okay, good. So each one of these had this inflection point. And the main problem was to get into this. Since it took until 1975 to get to the first step, we wasted another 5, 10 years for the second inflection point. And now the next one, fortunately, is going to take us until the year 2040. It began in 2015, but it's really not going to come to fruition until 2025 because of the human factor. So if you go to the first introduction of the concept, of roadmap, really didn't realize itself until 1975, when finally this element began to make sense. Gordon was very upset, and nobody realized, not the 2x every 2 years, that he had predicted in 1965 that we're going to have a personal computer that is portable, essentially. You're going to have control for the automobiles. You're going to have essentially what is an iPhone. And you're going to have a wristwatch and all this kind of stuff that he was projecting when the technology could only make 50 transistors. These were the point that he thought he was going to be remembered for, but that didn't happen. So if you look at this, nobody was paying attention to the semiconductor industry. But you see the red arrow? Well, bipolar crashed. If it was today, it would have been on the front pages, the end, we need a new switch. Fortunately, the new switch was already there. The new switch was 3 times bigger, 10x slower, but everybody embraced it because bipolar couldn't make a 4K. They failed, and so by default, people reluctantly adopted the MOS. So Gordon pointed out that there are 6 elements in making progress, and it's yield, he called miniaturization, if you go in his paper, die size, that he said there is no limit to die size. You can make a perfect devices. And then the way you design the device, the memory cell, the whole circuit. These are the 6 elements, and that's what he thought he was going to be remembered of. Again, he failed because nobody remembers him for this. So in 1975, it actually say everybody was beginning to talk about scaling. If you look at the red arrow, it's an irrelevant element. The contribution of scaling in obtaining what he marked from 1959 to 1975 is minimal. In fact, if you look at this, you can see that the major contribution is really on the design side, not on the technology side. So then, 1974, to create even more confusion, the NAR came out with these very useful rules that allow everybody that was halfway qualified to really start a company. If you look at the explosion in Silicon Valley, it went from 1 company to 50 companies between 1965 and 1975. That's the reason. Even somebody that knew, all you had to do, it was very simple. If you know how to multiply by 0.7, you're in business, okay? So we explained this, and people say, aha, now I understand. If I do the NARD, more comes automatically in this way. So if you really look at this, and you look at these elements, okay, and you look at what they have in common, they only have 1 element in common, but there is a fundamental difference. If scaling fails, all of this collapses. If scaling slows down, okay, so what? In fact, I'll show you that scaling, we have eliminated, as of today, scaling from the list. We don't need it. So don't worry about 3 nanometer. You don't need to do it in the first place, okay? But what people did, create this monster that they call Moore's Law. And so if I ask 10 people and I ask them, what is Moore's Law? They all tell me something different. Because every time there was a new product, say, oh, this is much faster because of Moore's Law. Or the die size is much larger because of Moore's Law. So we should confess that we misled you. Okay, but you voted for us, now you're stuck with us. Oh, I'm sorry, that's another speech. So, but Carver Mead already had identified that 5 nanometer was going to be the limit, for tunneling. And Gordon, come from Caltech. And so by 94, Gordon was getting frantic because he said, we're going to cross this. So he was calling Carver almost every month. And so that was going to be a crisis, okay? But nobody was paying attention. Remember the first 4 foils? Nobody was paying attention. So at some point he said, well, what can we do? Everybody's doing scaling and not thinking about it, right? Oh, so in fact, if you look at any presentations, to take, for instance, the roadmap, in 1994, he said, send the alarm, tell them that we're going to run into a wall. And I went to the roadmap, and you can see, look at the number to the right, it's 2010. We're going to do silicon gate. And I will not show you the foils that show that you go from nanometer to picometer. The gate oxide was going to go to minuscule numbers, okay? So with this in mind, if you look at what was published at the time, everybody believed that that was the thing to do, and nobody worried about to do something else. So in 1997, I had a great intuition, and instead of plotting the thickness of the oxide as function of time, I calculated the number of monolayers, and it showed that by 2003, we were down to 3 or 4 monolayers, and by 2005, we were done. And so finally, I got the attention of the audience, and I said, by 2006, we need to be in a completely different kind of scheme. Now, I presented this at the SIA board, and I got an instantaneous reaction, as if they had never heard about it before. So they say, OK, we know what to do. It has already been done. What we're going to do, we're going to rebuild the Bell Labs. So since I was in charge of the technology committee, I put together some numbers, and I say, sure, that's a great idea. Now, let me show you what it takes. It takes $1 billion. And I showed it to the board, and the board member reacted as board members react when they hear something. Oops. They don't want to hear. You say, who, what? And they all look at their papers. No, not me, okay? So now what do? You still want them to do something, but you have to convince them that they were right. So I developed this very nice graph in which I say, yeah, you were right. We need the Bell Labs. But we built Sematech, and we are now discussing what to do. We're going to build a new research structure for the 21st century, because I know where to find people that are very smart, they work for nothing, they have humongous resources. And so I said, we know how to find it, and we can get away with 40 million. And then we were very popular. Craig Barrett and I said, oh, we can get it done with 40 million. And we had to negotiate forever, because even that was a lot of money, okay? And so with this, we initiated the Focus Center. Okay, and also say, well, if we're going to pay for it, we're going to have the whole world paying for it. So I started the ITRS, and by then I knew many people around the world. So we started with and in a very short time, as you can see from April approval, already in July we had the first meeting. And this was the key point. We're going to have a methodology. We use the roadmap. Then we pass it on to the university and all the research consortia. And then eventually we get to the IC maker and the users. Normally in the past, this used to take 20, 25 years. We got to do it in half the time. So with this in mind, I also, this is 1998, I said, we're going to do this. Now, everybody said, no, this is a coaxial cable. It's not a transistor. Said, no, that's what we're going to do, you know, in section. Not a single element of this was in manufacturing, remember, at that point. So I had an enthusiastic reaction. Of course, this is impossible. I said, I'm on the right track. When I get reaction, it means they're really understanding. That was an accomplishment in itself, okay? They finally understood that something needed to be done. And so we took 5 poor people that were desperately willing to work 20 hours per day with minimal pay, go around the world, collect, ride night and day, and we convinced them that this was the key step in solving this problem. Now, one thing that you have to realize, all the university came flocking to this activity, and so that was very positive. We've never done this before to this extent. Salvation. Okay, let's see. Thank you. In addition, we had Sematech that was going to help us solve all the problem. In fact, this was from the Sematech board meeting. I was on all the boards, so the Sematech board meeting, and said the goal of Sematech is to realize the roadmap. And we built this beautiful concept, the red brick wall. There was, remember, 2006, we need to be ready. And by 2000, it was clear that nothing was working, okay? This was the results, because you cannot build it in one step at a time. This was very complex. You had to re-engineer the whole transistor. And so, again, I got a very good positive feedback in 2000 that, again, this cannot be done. So fortunately, what happens, we knew where to go, because we were not ready for a high-K metal gate. But we had a stopgap. Imagine deforming silicon. That was like, swearing, okay? And we said, no, you can deform silicon. Actually, things get better. And so this bought us another 2 or 3 years to really get the problem solved. So this one is another from a Sematech meeting. And you can see the board members had a very clear idea what Sematech could and could not do. They didn't like each other, to be honest, okay? So when it came and say, we need to integrate the transistor. You cannot just do a layer of high K, a layer of this. What's your opinion? Well, their opinion was very clear, because you are enabling the competition. Now, imagine, You had to re-engineer a transistor. You can do the modules, but you cannot do the transistor itself. And I saw people yelled out of the meeting, say, you are integrated. You're not supposed to do that. And so then I used my secret weapon. So Gilbert de Klerk, in 1973, was a visiting scholar at Stanford. And so if you cannot do it in one place, well, you go into another place. He lives in Belgium. He was not subject to the Sematech board, the SIA board. And I said, Gilbert, you can do it. So in July 2000, in a meeting for International Sematech in Paris, I said, I have a program that we can do. And I found other people that are really poor. They work for peanuts. And they're going to do all the integration in 2002. We cannot do it in Sematech. Fine, we'll do it somewhere else. So is everybody OK? And they say yes. And at that time, EMEC was called EMEC because it's inter-university. But then when it got with Sematech, they became IMEC because now they had to sound American, OK? And so when you go to Flanders, you ask for EMEC. When they cross and they come into the United States, they become IMEC. But they were a $70 million, clean room that served all the university in Flanders. That was their function in life. So then, as Philip already explained, we got reinforcement from DARPA that funded the right stuff. And so in 11 years, the goal, remember, do it in half of 25 years, everything was in manufacturing. So at that point, champagne was open. It's the moment to celebrate. And by the 2013 roadmap, I say, wait a minute. I took the same graph that I used for the gate oxide. I just changed the scale. And I said, we have another problem. This is 2013. By 2021, we're going to run out of space. Nobody wanted to hear this. And so once again, is that going to be another center? Yeah, that was, the NRI that I said, we had already put the seeds. Don't have to worry, already pay for it. So how do we solve this? I said, this is really a Manhattan time of project. Unfortunately, they said it in Washington, and everybody was scared. This is a Manhattan project. No. This is a project whereby once you run out to this space, you go vertical, like has already been shown. So you don't have to invent anything much. And so the question was, who's going to do it first? So now you have, again, to separate PR and reality. If this is the indication, who's going to be the guy that is facing this problem? Well, so everybody says, oh, the technology node don't make any sense. Well, don't make any sense in the mouth of people that talk about technology nodes. But if you look at the technology nodes and the flash people, they have been pretty much close to the technology nodes. There are people that claim are on the technology node, but in reality, they are 3x off the technology node. So you had to be the flash company were the first one to solve the problem because they were killing themselves. If you look at the number of masks, and these guys sell memory, they don't sell processor, right? They make little money. Not in the last 2 years, but normally that's what they do. They'll pay for the next 3 years. It always goes in cycle. So, and also they were running out of electrons. The smaller you make the floating gate, the fewer the electrons, so you get more problems. In addition, there was another problem that, as of 2003, frequency couldn't go up. And it was because Moore's law was coming to an end. So I took this graph from our friends from IBM, and I said, OK, we're coming to an end, but this is Moore's law and this is frequency. How do the two things relate? There is no relation. Moore's law is OK. It's just that we cannot scale using the NARDS approach because the power is too much. But it's once again, the human factor. Everything is in this pot that is called Moore's law. That many times doesn't make any sense. So instead of starting an activity on systems, there was already something within IEEE called rebooting computing. They have finally realized that the frequency was not going anywhere. And look and behold, they have to change the architecture if you want to get anywhere. So I made an agreement. I left the SIA board because 80% of the members are fabless nowadays. So they were not interested in technology. And so I was able to move it. I changed the name. The logo looks similar. And as of last week, if you go to this address, you will see the new 2017 IRDS that looks like the old ITRS, but it has 2 sections on systems that you didn't have before. So I did a hybrid. So we have already Japan and Europe join, and they're rebooting computing. And then I did a hybrid with the 3 societies that I wanted to keep really close: electron devices, communication, and computer. So we have on the IRC this group of people to really explain for the next 5 years what they should be knowing very well what they're supposed to do, but they're refusing to do it. So I had to make a major change. It was time for a new direction, something to explain to people what are we going to do in the future. But think about this. Everything is already done. So if I compare this to 1998, this is a slam dunk. It's just a question of doing it. You don't have to invent anything. You just have to do it. But now remember, who's the poor guy that is going to go to the boss and say, boss, I need to change the whole architecture. Are you kidding me? Okay, so we say, okay, we need to concentrate on these elements. And we need to do, this is preaching in 2013, okay, to this architecture. And Samsung heard us, Toshiba heard us, and so forth. But the best confirmation came from the guys that we train at UCLA, Kinan Kim, and then he just happened to be the president of Samsung Electronics, but he was Professor Ken Wang. And so, I said, hey, Kinan, how do you make decisions? It's simple. I walk in the staff meeting, I said, that's what we do. End of the meeting. And so he said, okay, we're going to go this way. Now, look at the beauty of this. He said, this is the design rule. We're going to stop doing the design rule, and we're going to go up. This is design rules. We're going to kill scaling once for all. Forget the slavery of being working with scaling. It's done. You don't need it in the first place. In fact, it was only 1 out of 6 of the requirements that Gordon Moore put out. And so if you look at this, it was simply this element. And so it had been retired, but non-volatile memory. So don't worry about 3 nanometers, so forth. You don't need to do it. So if you look immediately, the first reaction, the number of masks keep going down. And they say by 2022, you're going to have 1 terabit. And you see the number of layers that keep increasing at this rate. And if you look at this as ISSCC, February, this one already, experimental work on 1 terabit. So 2022 is in the bag. And if you look at the die size, very reasonable. 181, 182 millimeters square, half the size of a normal processor. So this is done. Now, if you want to talk about economics, let me explain this. This is the key slide. The blue stuff is I-line, introduced in manufacturing, 1992. So what I've been telling people for the last 5 years, if you have some old scanners in the garage, don't sell them. All these startup in China on 200 millimeter, don't sell them, keep them, okay? You're gonna use them. You can see the next one is 248, the orange. So 80% of this layer belong to equipment that was developed between 1992 and 1995. So it means very, very low cost. So why? Because you don't need to push scaling to the limit in the moment you go in 3D. Now, there was another element, and again, remember, you have to talk to a board, so you use a different language. So I was very careful to say that we were going to do novel and old CMOS devices. But that was too complex. So I said, we are looking for the new switch. Then everybody related to you're going to stay the old switch. You put the new one like we did with bipolar, and everything is going to be like before. OK, go ahead, do it. Well, it was close to reality, but it was not precisely what we wanted to do. What we wanted to do is to find all these guys that would work below 400 degrees C. So we had this plan, like already Philip discussed, to put them on top. Because that was the idea, how you can really avoid going from one chip to another one to the shorter distance. And given that people were doing 14, 15, 16 layers, you have to make them skinny that they can fit right on top where we put a VR normally. The only difference, you put one on top of the other, this memory, they just come for free, okay? So that was one approach. So that approach, it begins to be understood. The second one, I'm finding more resistance from the bottom. So in 2013, they asked me, I went to Semi-Japan, what comes after FinFET? So, well, after FinFET, what you can do, you take one of the fins out, you make it taller so you get more current, and then you remove another one, and then you make it taller. Now, when I make this prediction, I really don't know if that's what's going to happen. So normally I hold my breath, and it's very painful because this was December 2013. And I had to wait to breathe again until August 2014, when finally Mark Bohr said, you know what we're going to do? We're going to take one of the fins, make him taller, and that's what really happens. Then I said, okay, I didn't make completely a fool out of myself, and it showed that this was the approach. And you can see, how do you get gain? It's true that Dimitri did all this fancy work with the virtual sorts and so forth. This is very crude. You make the fin taller, and you get 25% more current. Okay? And if you make it taller yet, you got more current. So the performance problem, if you care about current, is very simple. You make the fin a little taller, and you're done. Okay? So if you look at the scaling factor, actually, when you really look at what the number is, you can see that as soon as they understood this game, already going from planar to FinFET, and then remove the fins, you get actually an accelerated scaling factor. Because if you do 2.8 in 3 years, it's equivalent to doing 2x in 2 years. So I'm embarrassed for the people from my old company. Say, I'm sorry, we are on the 2.5 years. Yeah, but you're doing 2.7, so actually, see, if you read the Moore's Law paper, it's still on Moore's Law. So I took all the design rules. Everything is published. And I look at this element. So I say, OK, the real limit, what people call 3 nanometer, is essentially a 10 nanometer technology. What can we do with that? First of all, you look at the disaster from a cost point of view. You look, first of all this gray stuff takes 3, 4 layers. It means the same to do 1 layer. You go 4 times. The tool costs about $60 million, so you go $240 million. And if you want to see the size of one of these tools, for $150 million, you can buy one of these. Tony, can we get a discount? Oh, OK, thank you. So what we're doing right now, we are in the middle of this phase, right? We can do more of it. It's not as good, and it costs a whole bunch more. So I took myself, I used to have a group that did analysis. So this is the 7 nanometer TSMC cell. I analyzed the design rules, and I look at what it is. And the smaller you make stuff, and the more you have line edge roughness. So you can tell the designer, you got a 10 nanometer gate, or maybe a 15 nanometer gate, okay? So it doesn't do any good. But if you turn it in this way, this is done by deposition, accuracy plus or minus 0.5 nanometer. So if you laid out everything, remember the fin, now you put it flat, is in this way, and with this, the area is about 40%. So if you do more of this, the other guys are going to do 300 layers, so you can do few layers. I'm highly electromagnetic. But I don't know. I have to give you the key slide. Hey, go to the next one. Go to the next one. This is collapsing again. I'm missing my clinch line. Mr. Projector, go to the next slide. Can you advance manually? Next slide, please. Oh. See what happens. It must be really important. If PowerPoint freezes, you know that it's important. Sorry, Hank.
No problem. Well, it is a problem.
That's what I normally do in my laptop because as I go forward, what I'm going to show you in the next slide is essentially, so how can you do 2x every couple of years? You learn how to do 2x by scaling by 70% linearly. But you can also do 2x adding 2 layers in the north direction every 2 years. Or you can stack 2 layers of transistor in the south direction. So these 3 methods, they all give you 2x every 2 years, and they are 100% independent from each other. Now, go to the next step. What if you combine them, since they are completely independent? You get to MIT. That's where you can see? So if you combine these, imagine this. What I'm going to show you, the number is, suppose you do scaling, okay, and forget, the last is 10 nanometer, okay? So if you do this, let me do the one before quickly. Okay, so if you look at these 3 methods, so you can double the number of transistors by doing scaling, or you can stack an additional layer of transistor and you get the same result, or you can do what Philip showed you, put this number of layers, and actually you can do a hybrid that the numbers become very reasonable, okay? And then if you put all of this together, then if you mix all these elements, you stretch something that was only 8 years into 16 years. And that justifies my 2040, okay? And so in the roadmap that you can get, you'll see that we've done the first step, and then the second step was scaling. And given the 10 nanometer, you can only buy today. That's my friend SML tell me. So that's what if people were really absorbing this is the universal layout, whether it's a memory, whether it's logic, and this is made by this. Each one of these is a stack of 2, 4, 8 transistors, and then the only thing you have to do is to connect them together. So the question is, given that this is so obvious, who's going to be the first one to move? And then you understand why this one has begun in 2015 for the memory guy. It's going to take another few years until the logic guys catch up, and then this is what we will be. Hank? Okay. Thank you.
Thank you. Okay, questions?
Yeah. I don't need the microphone. Being a circuit designer, not device physicist at all, I'm very intrigued by this vertical stacking. Do you need crystalline structures for that? And if you do, how do you get that crystalline structure as you stack up? You're not doing wafer to wafer, I don't expect.
No.
Are you depositing a crystalline structure?
No. I mean, the FinFET, the main breakthrough of the FinFET was that it's grown from the silicon. If you grow it very fast, it's polycrystalline. That's what the memory guys do. But if you grow it very slowly, it's single crystal, okay? So the basic element of because the FinFET is not an insulator. The FinFET touches the silicon. So it depends, if you only have to do 2, 3, 4 layers, you can spend the time, whereas the memory guy, they have to do it quickly, they do grow a lot of polycrystalline stuff. So it depends how clean this has to be, okay?
If I could interrupt a second, if you ask me the question at the right time, I'll tell you how you can stack any crystals.
See? That's my man,
Questions?
They're convinced.
So scaling addresses the density of the devices, and of course that's key economic drive. But in general, if we go out of the Dennard scaling, we abandon a look at the performance of the transistor itself. And what I mean by that is that you have a transistor that electrostatically may be very well behaved, but is burdened by increasingly more and more capacitance. I think the this issue was brought up earlier. So, I mean, we see it already. The FinFET has a lot more relative parasitic capacitance to the planar device that we had before. And with more and more nanosheets or nanowires, I can see that going even further in that direction. So what is your thinking about the significance of power scaling, which is left out of the overall scaling?
Yeah, so, first of all, everything is engineering. There is not this pure science that you do have this pure, new switch that you plug in. But if you look at the evidence of what they had done for the last 3 or 4 generations, okay? If you look at the average gain in current has been 10 to 15%. And the height of the fin has been about 20, 25%. So most of the current improvement has come simply by making the old way. You make the transistor bigger, you get more current. So that is very simple-minded, but that's precisely what they're doing. In the moment you turn it on the side, you make it a little longer. I calculated, actually, with the layout in this way, you save about, it's only 40% of the standard layout. So you can spend a lot of this accumulated 401k in investment in making the transistor longer. The other thing is, the gate itself, is 10 to 15 nanometer. From a design point of view, it's a killer. But I asked my friends from Applied, what's the accuracy if you make the gate? It's plus or minus half a nanometer. So just optimizing these 2 elements gains already a lot of performance that we squander in a way. It still doesn't eliminate the capacity and so forth, but that's why I'm saying we should have started at 10 nanometer or even 14 nanometer doing this, because we did a lot of work, very expensive, for very little gain. That if you were doing this, you would already have a lot of benefits. With this, you guys can come with the tunnel transistor, you can come with all the other elements. It's very easy, or carbon nanotubes, like Philip showed, you can plug and play with this. Once you had this basic architecture in place, you don't care what the transistor is. So there are a lot of improvements we can make. It's not perfect, but it gives you a new toolkit that at this point is very easy to replace parts. And you guys are very smart, so you'll tell me in the next in 2040 when I come back, and you tell me, see what I've done, and so I'll say, you guys are so smart, you did the right thing, okay?
Okay, it is time now for the next talk.